Recently, someone pointed out that I was ignoring hyperthreading in my performance experiments. It's interesting to think that 20 years ago I was doing tests against hyperthreaded CPUs to make recommendations as to whether we should leave hyperthreading on or turn it off on our servers, and I haven't thought about it much since. More on the reason for that later. For now, let's do some more experiments. I took basically the same experiments I was doing before, and instead of adding a constant value, I forced the system to fetch a value from a large array in memory. Doing this single-threaded creates no surprises. The addition of the random number generator alone is going to introduce some slowness, so we can't really compare this to the previous tests. If I then run 8 threads, which is the number of CPU cores on my computer, we see that each thread finishes in about the same amount of time as the single-threaded execution. No surprises there. However, when I run 16 threads, twice the number of CPU cores, we see an odd result. One would expect the loops to take twice as long, but they're slightly faster than that, and here we see the benefits of hyperthreading. Let's dive a little into what's going on. A modern CPU is pretty complex and has a lot of parts, but I'm going to simplify it quite a bit by just discussing the parts relevant to these experiments. A non-hyperthreaded CPU has 3 parts that we care about: the computational circuits, the on-chip memory, and the connection to the rest of the computer. The on-chip memory is split into parts such as registers and the L1 cache, but we're not worried about that for this discussion. The point is that the on-chip memory is very small but extremely fast. Accessing the on-chip memory is typically 200 times faster than access to the computer's main memory, but there's only about 512 kilobytes of it, depending on the hardware. Since the entire array can't fit into the on-chip memory, occasionally the CPU is going to need to request data from main memory, and it can take 100 nanoseconds before we have that data. All this time, the CPU is waiting patiently for the data, but the CPU could perform about 50 instructions in that time if it had data to work with. Enter hyperthreading. A hyperthreaded CPU has the same computation circuit and connection to the rest of the computer, but it has 2 sections of on-chip memory. What this means is that the chip can be keeping track of 2 threads of code at a time, even though it can only execute one of them at a time. Let's look at this in practical terms. If there's only one thread of code to be executed, the hyperthreaded CPU behaves exactly like a non-hyperthreaded CPU by only using one of its memory areas. However, if 2 threads are assigned to the CPU and each one is entirely compute-bound, meaning they don't need any memory access, like in the previous video where we were just adding a constant value, the hardware will switch between the 2 tasks, ensuring that each has equal time to use the computational circuits. This is why we see compute-bound workloads performing as if the computer has 8 CPUs. These most recent experiments expose the really interesting case. When a particular program stalls because it's waiting for something, the hardware can reactively switch to running the other thread. Some percentage of the time, the data needed by the other thread will already be on the chip, and that thread can do some work while the other thread is waiting. Of course, sometimes both threads are waiting for data from main memory, and this is why the speedup is generally reported at 15 to 30%, depending on the exact code that's running, and not any faster. So why did I completely forget about hyperthreading while doing my earlier experiments? Like many others, I've been working on software deployment to cloud infrastructure for many years now. Taking Kubernetes as an example, you have the hardware, then an operating system, usually Linux, abstracts the hardware. Then Kubernetes abstracts the hardware even further by running the actual code inside a container. It's impossible for any containerized program to know what other programs and other containers are competing for CPU time. Additionally, the containerization doesn't even guarantee that any information about the CPU type will be available for programs. Thus, the exact hardware isn't a practical concern of the developer, and hyperthreading is something that's the concern of infrastructure experts.